with Hatami and Shachar Lovett, my advisor. Okay, let's start. Let me start with a basic problem. Let's say you're given a 0-1 matrix, and this is the task. You want to partition this matrix into a few rectangles that are monochromatic. And what do I mean by a rectangle? I just mean a subset of rows times a subset of vertices. So they don't have to be consecutive. So let's say in this example, for example, these two things are just one rectangle. Okay? Now, a natural question to ask is, how many rectangles do we need to do this partitioning? And it turns out there is a very interesting and natural measure from computer science that roughly captures the number of these rectangles required. And it's called communication complexity of the matrix. So let me just quickly, roughly define what communication complexity means. So you can explain communication complexity in terms of a game. Let's say you have a matrix, it's n by n, and we can think of a two-party game. We have Alice and Bob. Alice has the index of a row, and Bob has the index of a column. So Alice doesn't know which index Bob has, and Bob also doesn't know what x is. And they want to figure out what is the value of the entry xy. Okay. And they want to do this by communication. So Alice sends a bit to Bob, Bob sends a bit to Alice, and they communicate. Well, the obvious thing is that just Alice tells Bob, says, hey, this is my index. It's index x. And Bob can, now that has both x and y, can just figure out what is. But how many bits Alice has to send to Bob? Well, it's roughly log of the number of rows here, just to send. Okay? And so with communication complexity asks whether there's a better way. There's some better way to send fewer bits so that they can compute this value. So let's say we have a protocol, they have agreed on a protocol that compute this function, and we call the communication complexity of this matrix to be the worst pair, the communication complexity on the worst pair that computes this function, this value. So you can think of this as actually just a partitioning of the matrix into a few monochromatic rectangles, but the partitions have a more structured style. They're not arbitrary. But it turns out that these structured partitions are basically very similar to the arbitrary partitions. So if you have a communication complexity of cost k, by that mean you have to send k bits, at worst case, to compute the communication complexity. This corresponds to roughly 2 to the k many rectangles. And this, that are kind of special. And if you wanted to come up with an arbitrary partitioning to monochromatic rectangles, this would be also, the number would be roughly 2 to the square root k, or something like 2 to the k. And it could achieve either case. Okay. And so, well, the communication complexity is kind of like a strange measure. We don't know how to think about it. And a natural question to ask is there a natural measure of a matrix that would capture communication complexity? And one such natural measure, One such natural measure of complexity is just the rank of the matrix over the row numbers. Because if we had the partitioning to rectangles, then well, each of these rectangles are a rank 1 matrix, right? If you just fix everything else to be 0 and just look at this part to be 1, that's just a rank 1 matrix. So the real rank of the matrix is just at most 2 to the communication complexity. And there is a famous conjecture called log rank conjecture that says this is basically tight. So if you have a matrix that its rank is something, the communication complexity is at most a polylogarithmic in the rank of the matrix. Okay. And we know this really cannot be logarithmic. It has to be polylog. So we have lower bounds that are 4 log squared. And the best thing we know so far is instead of polylog, we know square root of rank. This is the work of my advisor, Shachar. Okay. Well, so since the conjecture is difficult and people don't know how to prove it, there are simpler notions, like restricted classes of matrices that people are trying to understand. And one of these these special classes is called XOR functions. So let me just quickly explain what an XOR function means. We have a function, now it's defined on f2 to the n to 0, 1. So it just gets 2 values, 0 or 1. And we can naturally define a matrix from this function by just on row x and column y, which each one is taken from f2 to the n, you just let the value of your matrix to be just f of x plus y. So this plus it happens in f2 to the n. Okay? And now let's see what is the partitioning of our matrix to rectangles. Well, each rectangle now corresponds to let's say a rectangle AI times BI corresponds to a sum set, AI plus BI. And now we say, oh, our matrix is constant here. So that means the function is constant on this sum set. Okay, so basically I have partitioned my space of f2 to the n times f2 to the n to a few rectangles. And each sum set gets a constant value. Now, the previous natural question that I asked. Oh, yeah, okay. The question is translated to the following. Well, now what is a natural complexity measure of the function that would capture this communication complexity? And a very interesting measure for a given function on f2 to the n is called parity decision tree of the function. So let me just explain what parity decision tree means. So it's a model to compute the function. So let's say you're given a function on f2 to the n to 0, 1, and you want to compute the value of the function on a given input. So let's say your input is z, which is in f2 to the n, it's z1 up to zn. And the way you want to compute is every time you ask a question, which is just a linear equation in some of the bits. So, for example, in this question, you ask z, what is the value of z1 plus z4 plus z5? If it's 0, you go to the left. If it's 1, go to the right. So basically, every time you ask a linear character, and depending on the value, you end up in a leaf. And we expect that the value at every leaf should be constant. In other words, you somehow partition your space to subspaces that are all low codimension, and your function is constant on all of them, in this more structured sense. And this measure is called depth of the function to be the depth of the shortest parity decision tree that computes the function. Okay.
Sorry, where is f in this tree? I'm not.
Where is what?
What does this tree have to do with f?
This at the end has to compute the value of f. So this tree corresponds to f. For example, if this gets input z, okay, and then you ask a few questions, and at the end this leaf has a value of 0 or 1. So this 0 means f of z is 0.
I see. Thank you.
Okay. Now let's say you have a function that has a small parity decision tree. I claim that this very naturally translates to a very fast communication protocol for the corresponding matrix. How do you know the protocol? Let's say this is the tree, and Alice and Bob both have this tree, so they both know what the tree is. Let's say Alice has this x and Bob has y, and they want to compute compute what is f of x plus y, which was our communication problem. Well, we can just write this equation as of this form. So Alice has this part, right, because it's all the x's, and Bob has this part. So Alice, for example, can just send Bob this bit, it's just 1 bit, and Bob can send Alice this bit, which is 1 bit. So now they both know what is the value of this equation, and they so both together walk on the suitable path on the tree, and at the end they figure out what is the value on the leaf. So this translates into this formula. We say communication complexity of the matrix is at most twice the depth of the parity decision tree that computes the function. And it's a natural question to ask is whether this is tight, basically. So this depth is roughly just equivalent to this communication complexity. And in this work, we basically showed this. We showed that if you have a low communication complexity for a problem, you can always find a parity decision tree for the corresponding matrix. So this power is 6.
There are examples where it's polynomial, where you need the power.
Well, probably we need a power. Yeah, I mean, this are like 4 of it. Well, the thing is, okay, our result is more general. It's not about communication complexity. It's about all partitioning. To any arbitrary partitioning to rectangles. So you lose a 2 power of 2 there. So if, yeah, in the way, if even we had the best approaches, we would really need at least a 2. Okay.
So, sorry, so this can't be linear, or it can possibly be linear?
It can. If I'm saying if this is general rectangles, it's not just
Okay.
thing. I think that should be really a 2. Because that means then the communication complexity is really at least also a square of that value. But yeah.
You can say last, if here you need the power.
Yeah, sure. Yeah, sure. That, yeah. Okay, just going back to the parity decision tree model, this is just one observation that's interesting. This was given by Stan and others. They say to construct a parity decision tree for the matrix is really just enough to find one subspace of low codimension that your function is constant on. So what do I mean? I mean it's enough to find just one leaf in the parity decision tree, and that gives you the rest of the parity decision tree. Why is that? This is only true if the function has small Fourier support. So this is because if you have a function that has few Fourier coefficients, and you restrict it to a subspace and it's constant on that subspace, then in all the other cosets, the number of Fourier coefficients drops by 2. So you can just now restrict to each other coset of the subspace and iterate this argument. Every time you divide the number of Fourier coefficients, so at the end you get a log of number of Fourier coefficients in the depth of your tree. Okay. So really the goal here is just to find one subspace that our function is constant on. Okay. So now this has an immediate corollary. So what was Lagrange conjecture for XOR functions? It was saying that communication complexity of a matrix is at most polylogarithmic rank of the matrix. And if we're looking at these special XOR matrices, the rank of that matrix is just the number of non-zero Fourier coefficients. And the communication, so this is Lagrange conjecture. Now we know that this is at most a polynomial in communication complexity. So this corresponds to the following. Is equivalent. That the depth of the decision tree is at most polylogarithmic and the number of non-zero Fourier coefficients. And by the previous slide that I explained that it's enough to find just one subspace, then this Lagrange conjecture will be equivalent to the following. Can you find just one subspace of polylogarithmic codimension in the number of non-zero Fourier coefficients that your function is constant on. And just notice that this might not be really the best way to phrase this conjecture in terms of Fourier analysis, because the function really we care about Boolean functions, about functions, or at least things that are Boolean, or you can just wiggle the values a little. This is not true if you allow like arbitrary functions. They could take any value between 0 and 1. Okay, now going back to the main theorem, so following the things that I explained, now the theorem translates to the following form. If you have a partitioning of your space of f to the n times f to the n to a few products of rectangles, and you know that the function is constant on each subset, it can be defined as just one subspace that has codimension polylogarithmic on the number of rectangles. So k is just the number of rectangles. Everywhere I use k to be the number of rectangles, and such that your function is constant. Actually, after this line, you can just forget completely about everything I said, and you can just still follow the talk. And I won't use any things about communication complexity or anything. Okay, actually, I'm gonna stop for like 30 seconds, so you just maybe think about the problem, maybe you want how to solve it. 30 seconds is maybe more. We have time. Okay. Let me continue with the first failed attempt. So the most natural thing to say, oh, I have only like k rectangles, well then one of them must be large. So I just look at the largest one. And if I could have some results of this form, that if you have any two large sets, then their sum set should contain a large subspace. Then that would give me what I want, right? Because I know this one is large, and I just find a very large subspace right here that I know is constant. But of course, this is not true, and the so-called niveau set construction is a counterexample to this. So the counterexample is just take your sets A and B just to be a Hamming ball of radius around n over 2 minus square root n. So this is basically has a constant density, but A plus B is just a Hamming ball of n minus 2 square root n radius, which you can show it doesn't have any subspace of codimension less than 2 square root n. But we want codimension polylogarithmic in K. Okay. That I think is not known. I think the best known is you can always find like alpha times n. If alpha is the density of your set, then you can find the subspace of dimension. You can find the subspace of dimension now the second attempt is that, well, maybe I don't really need to find a subspace that's entirely inside one of these rectangles. What if I find a subspace that's almost inside one of these rectangles, one of these subsets? So when I'm talking about a subspace, I really just mean a subspace inside F2 to the n. But even though I show in this way, when I show this way, it's like a V. This is a subspace in F2 to the n times another coset of this subspace. Okay, just a representation. So what if we found a subspace that's almost inside the subset? By almost, I mean 1 minus epsilon fraction of the subspace is inside a specific subset. If I could pick epsilon to be very small, like epsilon to be 1 over just the number of non-zero Fourier coefficients, I would claim that I'd be done. Why? This is just a simply follows from uncertainty principle. Because uncertainty principle says, oh, if you have a function that is small, has small Fourier support, and it also has small average, because here we're talking about only Boolean functions. So having a small support in the physical space corresponds to a small average. Then we know that the function. So we know that the function should be 0 here, right? So if I have, because this times this is at least 1. Now I have a subspace that's its average is less than 1 over k because most of it is 0. So the only part that's outside of the subspace could be 1. So this naturally leads us to the following conjecture, that if you have two sets that have density alpha, and you fix the parameter epsilon, then can you find a subspace that has codimension polylogarithmic in epsilon and alpha? That's 1 minus epsilon fraction of the subspace is inside A plus B. And it turns out that this is a rather hard conjecture, and it follows. It's something that naturally comes up when one is trying to study Roth theorem or structure of just capset or structure of A plus A plus A. This is a natural question that comes up in all of these things, and I think it will have many applications.
Do we know it if you add more additions? Does it make it? If instead of A plus B, it was like A plus B plus C or something?
Yes. We'll talk about that.
So hang on, but if epsilon is fixed, is this topside this result?
Yes. Yeah.
So what is the dependence? I don't know what the dependence of topside this result is.
Yeah.
On the sun.
I'll write it right. So all we know is the following result of Tom standard, that the dependence on epsilon here is epsilon is outside of the polylog, and is epsilon to the minus 2, which just corresponds to the chain theorem. Application of chain theorem. But what we were really hoping for was an epsilon to be alpha, right? We are interested in this regime of epsilon being close to alpha. And then this is probably not the best way of phrasing this condition, because epsilon, if it's super tiny, I have no idea what happens. But we are really only interested in the case that epsilon is very close to alpha for all these questions.
You tested this for kind of Nevo set.
Sorry?
Did you test this for Nevo set?
Yeah, because Nevo said so. It's, let's say you have a Nevo set of density alpha, then A plus A is just huge. So you can just basically take your subspace to be the whole space. Because you just miss only. Yes.
What's the Nevo set? This thing of the hummingball half on that?
Sorry?
What is this Nevo set? The hummingball
Yeah.
radius?
It's the hummingball radius n over 2 minus a constant times square root n.
The alpha is like minus 2 to the minus c squared. So if you add 2 to those together, yeah, I guess then it becomes like 99%. It doesn't.
Yeah,
You care about the 99, but
Yeah, much more than 99%.
Yeah,
I've
you
done the
need
exact
one
calculations, but all you're missing is a Hamming ball of radius 2 square, 2c square root n.
So epsilon and alpha
started
compare
with n over 4 possibility.
But that is tiny, so n over 4 plus.
I'm saying that even if you would have started.
Oh, yeah,
with
sure.
4 factor, you still would
Yes. And the thing is, I think this has other applications. For example, let's say you want to prove that a similar result, like a Bogoliv proof type result for a plus a plus a. Then you say, oh, if a plus a is not everything, then a plus a should have density less than 1 minus density of my set. Otherwise, you could just use pigeonhole principle to say a plus a is everything. So this is a rather stronger conjecture.
So for applications, it would be just as good to have a fourfold subset name, not to worry about already for sums.
Sure, for which applications?
Well,
Not worried.
not for this one, but where is 3 element
Yeah, I mean, I don't have a specific application for this, but I'm just saying if you want to have a result for a plus a, this is out of curiosity maybe. And, well, okay, there are some other connections also. The thing is, all we know, was the question of was, is the following, that if instead of a plus a, you're looking at a plus, looking at threefold subsets. So you have three sets, a, b, and c, and look at a plus b plus c, then you have the following very nice result of shown in CSASC. That they find a subspace that is almost entirely equal. And it's code mentioned. I don't know, you don't remember the exact, so probably it's like 6 or something. And the thing is, the result is actually stronger. So they say instead of just there exists one subspace, they say there for 99% of the translates of a subspace, all of those translates are mostly inside a plus b plus c. And they use this result to prove Barron type upper bounds for sets with no solutions to the following equation: x plus y plus z equals 3.
Sorry, if A and B and C were the same small subspace, when you add it 3 times, it's a small set. So it's not that you get 99%
Of a subspace. You get this subspace. You get 99% of a subspace.
of that. That's what this is saying, but the translates of the sub. So the statement you said about translates of the subspace, I don't understand that.
So you don't understand this or the?
I think maybe I misheard
So
you.
okay, so the exact.
I don't understand.
You say there is a translate of a subspace. You say there is a subspace of codimension polylog alpha 1 alpha minus 1, such that a translated subspace intersection a plus b plus c divided by size of is greater than 1 minus epsilon.
So how many of these do you find? Just one, or you find lots of these?
I think all of this here, but I think you can say that for many x, so x belonging to a set S, so the size of S is roughly like 99% of B or something. I think. And this is from a very long time ago.
Is it not the joint or so?
These are translated to a subspace. These are the closest of a specific subspace. And they don't have to be additional. I'm just saying there are many x. So most of them. I'm counting the things that are in this subspace again. So I'm not saying there are these many cosets.
Talking about F1.
Good point. So, yeah, in all of the things that I've talked so far, everything is affine. Yeah. So it seems that really structure of A plus A, or this conjecture would correspond to, or it would give a better understanding to Baron type upper bounds for just Roth theorem.
So just by pigeonhole, like you said earlier, for the last time. For this, I mean, the fact that this implies that there are type bounds, all you're using is pigeonhole for the last part.
For this, yes, I think. Yeah, you say if A plus A is not everything, then it misses the 3 times A, and then. Okay, now
So would that conjecture lead to also some Baron type result for Ross theorem?
So I haven't really done the details, but I think it should. Maybe if you have a I'm saying this as it is doesn't lead to Baron type things for Baron type software. You need this 99%. So we have to make a conjecture that would be like a 99% of the translated subspace probably, and then you want to say that. Yeah, I'm not sure. I have to really.
Yeah,
Actually, very recently I found a blog post by Gowers from very bold ones from 2011 that he talks about approach for Roth theorem, and he naturally talks about if you have A plus A has density less than 1 minus alpha, then what happens? Can you give a density increment? And so yeah, he was discussing that crude CSAS type methods really don't work at all. Okay, but so we really cannot prove this conjecture. But we have something much stronger. We have a different setup. We not only just have one subset, we have just partition our space to all of these subsets. So we somehow want to utilize this entire partition structure instead of just focusing on a single subset. And this is let me quickly mention. So the proof is very short. I'll just first explain the general sketch and then just give the proof. So, okay, again, what is the goal? Find a subspace that has codimension polylogarithmic in the number of rectangles. And my function is constant. So I claim the following is true. To prove this, it's really just enough to find a subspace that's, again, has this type of codimension, that its average is slightly different than the global average. So if I restrict my functions to this subspace, its average changes by a little bit, like the global average function over the whole space. I claim that this is enough. And you don't have to go down by a very big difference in average, just to like a 1% difference is enough. So, modulo this claim, let me just explain what is the general approach if we knew how to handle this case. Let's say you start with a function, and we can just, without loss of generality, assume that our function has average more than half. Otherwise, just flip all the bits or something. So we know average our function is half. The first step is we want to find the density decrement. So we find the subspace. First of all, even though the average is more than half, we know that there is still a large zero rectangle, because we know that there is a portion of the space that is zero. Otherwise, we could still just directly apply the uncertainty principle and say, oh, your function just has to be completely constant. So we still know that there is a zero rectangle. And so let's say this is the one. And now we just use what we have. So we just have Sanders result. So we just find this subspace that has average less than half, for example. So So 75% of the subspace we are sure is inside this subset. Okay. And so the difference now between average of F and average of F restricted to the subspace is like 25%. Right. Now, I want to argue something like this. I want to say that, so this was my subspace. Now I just look at all the cosets of this. And I want to claim that this partitioning structure of these rectangles typically should get simpler when I restrict to a typical coset here. So I should now explain what do I really mean by simpler. So that is the goal of the rest of the topic. What do I mean by picking a typical coset and say, oh, my partition structure is much simpler here. If we assume that we have such a thing, then we can just restrict to that coset and continue. So let's say I found this coset that my partition is kind of simpler, and I could just restrict to this and continue until it's so simple that it's just constant. So all I have to explain now is what do I really mean by simple. Okay. So that's, I have to define.
So you mentioned subspace. You want to find this a subspace of the first one that you found.
It's a coset of the first one that I found. Did we mention subspace? The one that is completely constant?
No.
Yeah. The one that gets simpler, that one. Okay, so now let's say our matrices are indexed, are rectangles. This is a rectangle 1, 2, 3, and so on. And say we have I define a random variable. I just pick a random row and a random column, and I just pick a random point in the matrix. So my random variable is just picking a random, uniformly random, independently. So these are my random variables. So by this pi, I mean the index of the rectangle that contains my random point. So in this example, my point landed here, so pi is 5. And by this x tilde and y tilde, I mean the coset of the subspace that my point lands on. So x tilde says that x landed on coset x tilde, s plus x tilde, and y tilde plus s is where the coset that contains pi. Okay, so these are on this quotient. So what do we know? We know that the function has an average more than half, but we know that if I knew that x tilde is y tilde, then my function has average less than 25%. Because if I knew that x tilde is y tilde, I would know that my function lands in one of these diagonal cosets, where when you add this plus this, you just get v, and I know that my function on v has low average. So what do I want to argue is that this should tell me something. It should show that this joint random variable, x tilde, y tilde, gives me some information about this random variable pi. In other terms, the mutual information between x tilde and y tilde and pi is bounded from below. So basically the main lemma that I want to explain is the following. If you have any function, and you can find the subspace, not any function, a Boolean function. If you can find a subspace that gives you a slight difference in the average, then this random variable that I define, conditioned on this joint random variable, has a lower entropy by something like epsilon squared. So this is basically the only part that I have to explain, and that would just finish the proof, right? So I'm just gonna, this is technically just really one line, and you can just prove it using like middle school probability, elementary school probability, depending on middle school or elementary school. So what do we have? We start with this epsilon, giving a lower bound for this difference in the average, right? So let me just write this in other, which means just another way of writing is you have this random variable, and in this case you have the random variable, but you condition it on x tilde to be y tilde, so we know that x plus y lands in V. Okay, so this is just the average. Just to rewrite this average is basically just the sum over the one rectangles, the rectangles that get value 1, but I really don't care, I just sum over all the rectangles. So probability of pi equals t is just the measure of the specific rectangle, t. Okay. And I look at the difference of this measure with this value, which is just the average of this w was this quotient. I think I didn't even. So you pick a w and you fix x tilde and y tilde to be w, and you say what is the measure of my rectangle t in that particular coset. Average of all. This is definitely a upper round down difference. Now let me just rewrite this. What is this really? Just write this with Bayes' rule or whatever it's called. So this is just now x tilde equals y tilde. That will condition on pi being t multiplied by this. And now this is the crucial point is here that since we really had a partitioning to rectangles, this means that this random variable x tilde and y tilde, even when you conditioning on the random conditioning on fixing pi, are still independent. So you can just rewrite this as the product of x tilde equals y when you fix rectangle pi, product of the other side. All right. And this was also independent, so I just separate these also. So now, what is the next step to do? It's basically just separate out these two. So this is multiple. You can, for example, use an inequality like 1 minus AB is less than 1 minus A plus 1 minus B. And this is just it. Okay. But now I multiply back this average thing, so this is just this probability. So I just multiply those back again. What do I get? I just get the total variation difference between this measure. So it's like a product distribution and its joint distribution. And so I have two random variables. I look at the total variation difference between its product distribution and the joint distribution between these random variables. This is for the side of the rows, and I get another one for the side. And there is a, okay, this is probably the only part that's not in middle school that you can use. You can use there is an inequality called like Pinsker inequality that if you have some probability distribution, you have a lower bound on their total variation, then you can get a lower bound on their divergence. And where in this particular case, because of my distribution, you get a lower bound on their mutual information. So this is directly applying Pinsker inequality, and you just do this, and you're done. So what do you get? You get a lower bound on the mutual information between this random variable pi and this joint distribution x tilde and y tilde, which basically just translate to my previous formulation, the entropy of the entropy of this random variable pi when you fix Oh, well, not really infinite. I mean, when your condition on it still until drops like this.
So the entire argument is log free until the very last step you apply this.
Okay, so what did I do? I applied Sanders' result as a black box, right? So the subspace V. I'm sorry, I shouldn't use this V2. This is the S subspace that I mentioned. So the codimension of this is log to the 4 by applying result of Sanders. So that's the 4 you lose there. Then what did I do now? Okay. So here, every time I reduce my entropy by a constant, but I have to do this log of k times, because it's random variable. I have k many rectangles, so its entropy could be at most like log k. So to drop that down to 0.
So even in this lemma, can you give me some intuition why log come? I mean, log doesn't come in until the very last step in the proof.
Why do you have to do log many steps to reduce the?
So if the next slide, the entire calculation, there are no logs in all of these steps except for the very last one.
Yeah, well, I don't know. That's the magic of entropy. So, yeah, so I mean, it's just the relation between divergence and total variation, which is just the log of average of log, right?
So you apply this lemma with epsilon as constant, or?
Yeah, you can just pick epsilon to be 25%. So you apply this 1 log k many times again, so now we have 5. But now we have only found one subspace that is constant. So to get this parity decision tree, we have to apply this whole argument again log k many times to get to log to the 6. So yeah, this one quickly question is really, what does this problem? Can we solve a similar version for in the case of randomized protocols? So if you have, it's like a 99% of the previous problem. That if you have basically if you have now a probability distribution over these partitioning to rectangles, and can you get a probability distribution over partitioning to subspaces that somehow agree with your function? Yeah, and the thing is, basically all the steps that we have made breaks down because we can't really, if you know a sum set is almost monochromatic, you really cannot hope to find a subspace that's almost monochromatic using Sanders' result or something. So it really looks like it requires other ideas. Thanks.
So you mentioned that the result of Schwann and CSS that they use this type of thing to get Baron type lower bounds, right? So is it possible, do you think, to use this approach to get similar bounds, but when you, instead of density versions, you have coloring versions? Like you color your integers with many colors and you want to say that all of them are arithmetic free or some free from solutions.
Oh. Yeah, it's a good question. I don't know. I think this. Yeah, I mean, it's a natural question. If this type of entropy decrement is useful in any situation that you have a partitioning of space to some nice object instead of just having one object and restricting to that. But yeah, I don't know.
This might be a very naive question, but if you've got one dense object, you can take random translates of it to cover the whole space efficiently.
Okay.
So presumably that you can't then deduce anything from that about your original set from what you've done. otherwise it would contradict their examples. But I'm sort of struggling to.
For this randomized version, you say?
Well, if I've got a dense subset, say about 2 to the n,
Yes.
I only need kind of n translates of it to cover the whole of that 2 to the n. So I'll have a result about colorings. I can deduce a result about an individual set,
I see.
as long as the result is translation invariant. So I assume that what you've done doesn't give me anything that I didn't already know. So
It's a partition.
Yeah, the thing is we know
Don't
is
just have other partition.
but you can make a
Partition by rectangle. So if you take subspace, yeah.
now I want to find the partition by subspaces. It's not. Yeah, I don't know what.
I just somehow in many problems, the partition problem and the density problem are the same for that reason.
But we also want to partition the zero part of the function. So I mean, it's not just the part that the function is one. It's also the zero part. Also, that part is also completely structured. We also partition that part also to subspaces.
But we can discuss after.
Yeah.
I must have misunderstood some aspect.
Okay.
Any other questions?